Now let's talk about a specific technique by which we can convert a truth table, given truth table, into its optimized, minimized. I should say minimized in yeah, not the optimized, minimized Boolean expression form. So our target problem is this: like we have been given with a truth table. From that truth table, I need to determine the function in terms of minimized Boolean expression. In the terms of minimized Boolean expression. We all know from the previous slides that given a truth table, we can express function in terms of SOP, right? Sum of product, sigma m something, and which we can expand to its corresponding mean terms, and which can be really huge expression. And from there, we can apply our identity rules to kind of step by step make it minimize, and get into a minimum equivalent Boolean expression form. That's one way. This technique, Karnaugh map technique, makes that process faster, okay, by exploiting visual effectiveness of human being. Okay, we do we can do things visually in forms of tables and charts and grouping them with drawing and stuff like that, instead of like start applying all these all these identity rules to make and minimized expression, right? Also, if you think that, okay, in terms of this applying identities to minimizing expression, this is more or less ad hoc measurement, right? It depends on how practiced you are, how experienced you are. There is no like hard and fast rule that you can actually follow to step by step to get into some minimized equation. It's kind of your intuition that, okay, you apply identity 14 versus 11 versus 2, who knows, right? There can be many ways to do that. So identity based expression reduction is more human in nature. It does not follow any algorithmic steps or predefined process that how you want to do it. However, this Karnaugh map, as we will discuss, its target is to give some guidelines, step by step guideline, exploiting humans' visual uh, pattern recognition capability to make to get a minimized expression very fast without even applying identity rules and stuff like that. Secondly, this Karnaugh map is basically a stepping stone towards founding some advanced algorithm for Boolean expression minimization problem. Okay, as I said, like in real complex digital circuit, your Boolean number of variables in the Boolean function can go like hundreds easily, like 100 variable expression. There is no way a human can go and optimize and minimize that problem. However, if we can make certain algorithm step by step guidance, how can we formally, through some predefined steps, minimize the whole expression? Then it would be easier to implement just a computer program which then can just give us an minimize certain given arbitrary expression and give us the minimized version equivalent expression of that. Karnaugh map technique provides that stepping stone. It's that fast algorithm we can build up and implement in the computer program to make Boolean reduction. Of course, it is not used directly in computer design system, Karnaugh map, there has been developed many other advanced technology and algorithms to minimize Boolean expression. But their stepping stone start point was always this Karnaugh map. Then it was kind of evolved and derived and made it more effective, stuff like that in latter point of time, which are unfortunately out of our course scope. So we'll limit ourselves on the K-map, like aka Karnaugh map. In short, we call it a K-map, and we'll just try to understand this concept of algorithmic steps, and probably we can start thinking in terms of what algorithms we can make out of these. But let's first learn about this process. It's a visual technique, as I said, to reduce Boolean expression into Boolean expression given in a standard form. That's the first criteria. You cannot just give arbitrary Boolean expression into that technique. You need to express your function in terms of standard form, either SOP, POS. We'll focus on to the SOP in this case. This technique was first introduced by Maurice Karnaugh in 1953. Pretty old technique, still relevant. It was a refinement from the Weytig diagram, which is developed by Edward Weytig in 1952. And as I said, we usually call it a K-map technique. So what is this technique? This technique involves constructing tables. Okay. So let's say we have a function of two variables. Then we construct a 2 by 2 table. Okay. And what we do, we in the table, one like let's say this is column is marked as x, variable x, and rows. No, this is rows. The rows are marked for variable a, columns are marked for variable y. Just make the marking, and then we put the possible values to be done can be assigned on the x. So since x is a Boolean variable, we assign 0 and 1 in these rows. Similar for the columns, we assign 0 and 1 for the columns, and then inside this table cell, or I frequently call it boxes, inside this table cell or these boxes, what we make an indication of the value they make by combining x and y. So this box, the box marked as 0, why it is 0? Because its x value is 0, y value is 0, that is 0, 0 is 0. The box marked as 1, which why it is 1? X is because x is 0, y is 1. So its equivalent is 1. Similarly, box 3 is x is 1, y is 1. So we mark this box 3, 1, 1 is 3. Now, 3 variable K-map table are constructed in this way. It becomes like a 2 by 4 table. Okay. So on the row side, we marked it for variable x, and column side, let's say we mark it for variable y and z both. Then x can assign the value of 0 and 1. They can take the value. Now we need to see what the different value combination y and z can get. Okay, so they can have 0, 0, 0, 1, 1, 0, 1, sorry, 0, 0, 0, 1, 1, 0, 1, 1, right? That 0, 1, 2, 3, 4, 5. However, we mark them in a little bit different way. We mark them in a fashion that only one bit change between them. So we go from 0, 0 to 0, 1, then to 1, 1, then to 1, 0. So we write in this fashion, okay, 0, 0, then one bit change, 0, 1, then another bit change, 0, 2. So at each transition, only one bit gets changed. Just imagine if I had 0, 1 and then third column as 1, 0, then of course 2 bit has been changed. The MSB changed from 0 to 1, LSB changed from 1 to 0. So we don't want to make it happen. So we write down this combination in such a fashion, each column from column to column there is only one bit changes, and this pattern of sequencing is known as gray code. A gray code is a binary uh, is a binary representations in a sequence such that from one combination to another combination transition involve only one bit change. That's the gray code. So this is 3 variable K-map. This is 4 variable K-map table. It is 4 by 4, total 16 boxes. And let's say our variable is wxyz. We in the row side we write wx, column side we write yz, and we make their possible value binary value combination in a gray code, both in the rows and columns. And then we combine these bits to make index of the box. Like for example, like this 13, right, which is like for this box marked as 13, we have a wx11 and yz as 01. So 1101 is 13 in decimal. So we index that box as 13. That's how these indices are made. Now you might ask why we are doing a gray code fashion indexing of the boxes. To understand that, we need to understand the core principle of K-map reduction, K-map based reduction. So what K-map based reduction does is the group the minterms which are neighbor to each other. Now let's explain what is a neighbor term, or what I mean by this a minterm neighbor to each other. If you imagine these boxes belongs to corresponding minterms, like box 0 for minterm 0, box 1 for minterm 1, box 3 for minterm 3, and so on and so forth. So each box belongs to corresponding minterm as the box index suggests. Then in this table, 4 by 4 table, for example, if the boxes are neighbor to each other, they sit beside each other, then we call those two minterm as neighbor. Like in this example, 5 is neighbor with 7, with 1, with 13, and with 4. 15 is neighbor with 7, 14, 13, and 11. Now this is the definition of the neighborhood of the K-map boxes, and thus this goes into neighborhood of the minterms. But why so? Like, what is the advantage of doing that? Let's look at this. Like, let's take an example of 5 and 7, right? So we see the 5, the boolean values for wxyz is 0, 1, 0, 1, and for the 7 it is 0, 1, 1, 1. So they make only one bit change, right? Like a gray code. They are also, because we are following the gray code in that sequence, indexing sequence for row and column, neighbors are a gray code sequence. They only change one bit between them. You can test 5 and 1, right? 5 is 0, 1, 0, 1, and 1 is 0, 0, 0, 1. So number of bit change between them, those two patterns, is 1 bit. The MSB change, not MSB, the second bit, second part MSB, change from 1 to 0, and you become 5, M5 and M1, right? You transform M5 into M1, and they becomes a neighbor. Now let's understand what neighbor identification will give us advantage. Okay. To do that, let me just give you an example. just let me just make a text document. Kmap. All right. So we said that M5 and M1 are neighbor, right? Now M5 is W bar X Y bar Z, whereas your M1 is W bar X bar Y bar Z, right? Now by then, if we identify this neighbor and if we say, okay, let's group them, M1 and M5. So M1 grouping means grouping via OR operation always. So this is basically this or this, right? And that essentially become W bar Y bar Z X bar or X, which is W bar Y bar Z and 1 equals W bar Y bar Z. So if we group these two neighboring minterm, we have a way to reduce them, at least eliminating one term, right? Now make this group. How about 7 and 3? M3 and M7. Their neighbor. So we know M3 is W bar Y bar, W bar X bar YZ, whereas M7 is W bar X Y Z. Now if I group this M3 or M7, then we get similar way. Their neighbor, we are grouping them with the OR, and it become like W bar YZ X bar or X equals W bar YZ or 1 and 1 is W bar YZ, right? So this is the neighboring concept. All right. Now, so from the K-map, we see that, okay, we can identify the neighbors of the boxes, right? However, if we follow that definition of neighbors, means whose indices are differing by 1 bit, then 0 is neighbor of 2, right? They are differing by 1 bit. 4 is neighbor of 6 as well. 12 is neighbor of 14. 8 is neighbor of 10. Similar fashion, 8 is neighbor of 0. 9 is neighbor of 1. 11 is neighbor of 3. And 10 is neighbor of 2. So this edge column, these edge columns are neighbored with each other, and edge rows are also neighbored with each other in this table. So we can imagine this kind of a like a donut, if you would like this. Let's start with an like piece of paper and we roll them. These edges, they are neighbor, and then we again roll it like a donut, and those edges become like neighbor with each other. Just and pictorial representation of that idea that your edge rows, edge columns and edge rows are neighbor, those boxes are neighbor with each other.